For our physics project, we created a pulley system with a skateboard wheel, a string, and this highlighter. And in our video, we're going to show you how we found all the forces acting on the system and the energy transformations in the pulley.
3.
So we decided to approach this problem with an energy lens because we know energy is always conserved. We know the sum of the initial energy is equal to the sum of the final energies, and that the potential energy in the highlighter is transformed into linear kinetic energy of the highlighter and the rotational kinetic energy of the wheel. So we know that the potential energy of the highlighter is equal to the linear kinetic energy plus the rotational kinetic energy plus the thermal energy produced by friction on the wheel. And we know all our equations for each of these, and we know that the thermal energy is equivalent to the work done by friction because the string is doing work on the wheel. And once we plug in all our values that we've got from tracker, which was the acceleration is equal to 1.93 meters per second squared, and the final velocity is equal to 1.304 meters per second, and that the angular velocity is equal to 12.5 radians per second, we end up with the value of 0.109 joules for the work of friction, which is equal to the dot product of the force and dy, which is equivalent to the 0.16 meters that the highlighter drops. And we also ended up with a rotational kinetic energy value of 0.0703 joules.
All the forces acting on the pulley using a dynamics lens and an angular dynamics lens. So we know that the sum of the forces equals mass times acceleration, and in this case our sum of the forces equals the force of gravity minus tension minus the force of friction, because we labeled the downward direction as positive. So the force of gravity would be positive, and then tension and the force of friction are negative. So the force of friction, as we stated before, equals 0.177 newtons. The acceleration, according to tracker, is 1.93 meters per second squared, and the force of gravity equals 0.336 newtons. So we changed our equation around to be in terms of tension. So tension equals negative mass times acceleration minus the force of friction plus the force of gravity. So we plugged in all of our values, and we found that tension equals 0.094 newtons in the upward direction, which is the negative direction. So moving on to angular dynamics, when the pulley is released, the highlighter accelerates in the downward direction. So there is a torque being applied from the force of gravity on the wheel in the outward direction, so out of the board. So for angular dynamics, we know that the sum of the torques equals moment of inertia times alpha. So the sum of the torques equals the force of gravity times the radius minus the force of friction times the radius equals moment of inertia times alpha. And when we plug in our values, we find that alpha, or angular acceleration, equals 4.45 radians per second squared, or per second squared, and those are all the forces.
So here's all of our data that we have from tracker. This is all for the highlighter, and we also made 3 graphs. So we made a velocity versus time graph. The graph makes sense in general because, as you can see, the y component of the velocity is increasing steadily over time, and that's because the acceleration is constant. Underneath here we have a kinetic energy versus time graphs. The kinetic energy increases, the kinetic energy of the highlighter increases over time as it falls. A power versus time graph over here, and that also makes sense because power is the rate of change of energy over time, and so since the kinetic energy increases, the power also increases. And then we also have graphs and data from tracker for the wheel. So this is all of our tracker data for the wheel, and there you can see that. And then we also made graphs. We made similar graphs. We made a displacement for x and y versus time graph for the wheel. This is so that you can tell that the wheel is rotating in a circle. And then we also have a force acting centripetally versus time. This is another way you can tell that there's centripetal acceleration on the wheel, so it's rotating in a circle. We also have a rotational kinetic energy versus time graph and a angular velocity versus time graph, and this angular velocity is increasing steadily, thus the acceleration is constant. And our final graph we have is a power versus time graph. And you can see that that corresponds to the rotational kinetic energy versus time graph because it's gaining energy, so thus it has